Hi everyone, this is Pranjal Dutta from Chennai Mathematical Institute and a visiting research scholar at IIT Kanpur. Today I'll be talking about border depth circuits. This is a joint work with Prateek Dwivedi and Nitin Saxena, both from IIT Kanpur. So let's start. The basic question in theoretical computer science, or mainly computational complexity, is to prove P not equal to NP, and Valiant defined algebraic P versus NP, which is VP not equal to VNP. Back in 2001, Mulmula and Sohni proposed GCT1, Geometry Complexity Theory 1, to prove this VP not equal to VNP. In fact, the paper defines border complexity, which is also independently defined by Burgisar in the same year. And in this talk, we will be only considering the algebraic notion of border complexity. There are different notions of border complexity. Almost all are equivalent, but for the sake of simplicity, we will be talking about algebraic notions. So I'll define algebraic notion of border complexity, VP, VNP later. So what's the basic goal to propose geometry complexity theory 1 or geometry complexity theory? To prove complexity theoretic lower bounds using algebraic geometry representation theory. This was concrete. This was more concretely and explicitly written in GCT2 paper by the same Mulmula and Sohni back in 2008. Okay, so what's the basic model of computation? It's algebraic circuits. What is an algebraic circuit? It's a directed acyclic graph where the bottom nodes are just variables, and in between you have addition and multiplication gates, and ultimately it computes a polynomial, multivariate polynomial. Size of the circuit is the size of the graph, which is number of nodes plus edges, and size of the polynomial f is the minimum size of the circuit computing f. Many circuits can compute the same polynomial. We'll take the minimum size of the circuit, and depth is the longest path from bottom to top. In this case, this is 3. I give this example because we'll be talking about the 3 circuits later. Okay, so now once we have defined the model of computation, let's see what are the easy polynomials in this model and what are the hard polynomials. So VP variance P is one of the most important classes where we say that a sequence of polynomials is in VP is if both size and degree are polynomially bounded. One example is x1 to the n plus blah 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 plus xn to the n. Okay. Now another example of easy polynomial is the determinant polynomial. So how do you define the determinant polynomial? There is a take a symbolic n cross n matrix where each entries are new variables xij and define determinant of xn the obvious way. Now it is known that determinacy is universal. That means any polynomial f can be written as a linear projection of determinant. Since any polynomial can be written as linear projection of determinant, you can talk about the minimum dimension of the matrix which computes f. We call it determinant complexity. To give you an example, take this monomial x1 dot xn. This has determinant complexity n, you can show. Okay. So once you have defined this measured determinant complexity, you can define a class VVP like you defined VP variance P. And what is VVP? So it has all the sequence of polynomials Fn, which is polynomially bounded determinant complexity. Since determinant has small size circuit, it is obvious to show that VVP is inside VP, but it is not clear whether they are separated or whether they are equal. So now, once you have defined easy polynomials, let's define what is a hard polynomial. Okay. Or what do you mean by hard polynomial? So we say that Fn is hard if it requires super polynomial size algebraic circuits, or in fact, you can also set super polynomial size determinant complexity as well. The question is, are there hard polynomials? Yes, any random polynomial in fact is hard, but of course the challenge is to find an explicit one. And by explicit we mean the coefficient should be easily computable. Okay, so there are many hard candidate hard polynomials, but one of the most important polynomials is the permanent, and permanent is essentially determinant without signs. There is no plus minus, all are plus. Now, similarly, as determinant, permanent is also universal. That means any polynomial f can be written as a linear projection of permanent. And since this is universal, you can define the minimum dimension of the matrix computing a polynomial f, and that is permanent complexity. So once we have defined permanent complexity, we can define a class called VNP. And what is VNP? Like VP or like VVP, we can define VNPs, all the sequence of polynomials, which is permanent complexity polynomially bounded. Since VP is inside, so it is not hard to show that VP is inside VNP. Okay. So then we have the following sequence of inclusions: VVP is inside VP inside VNP. Of course, the conjecture is that VVP not equal to VNP and VP not equal to VNP. Equivalently, determinant complexity and algebraic circuits computing the polynomial permanent both should be super polynomial. In fact, it is conjectured to be exponential, but we are fine if we can prove super polynomial lower bound. So once we have defined these algebraic complexity classes and so on, let's dive into GCT and border complexity. So what is border complexity? So we will define border complexity of polynomials via approximative circuits, which we'll define in the next slide. Just to remind you, so these border complexity notion, border ranks, and so on were already defined before these definitions via approximative circuits and so on. For example, this border tensor rank is a very important notion, which is very closely related to matrix multiplication exponent. But as I mentioned, we'll be only talking about algebraic definition via this approximative circuits. Okay, so if you remember that the way I defined algebraic circuits, it's an acyclic and directed acyclic graph. Now it's the same thing, but think of this epsilon as a variable, but you can use it freely in the sense that there is no cost on using epsilon. So for example, in the edge, you can use 1 by epsilon cube. So in the edge, you can use any rational function on epsilon. And if you do that, ultimately you'll be computing g of a polynomial g x1 of xn over the field f of epsilon. Okay. Now, once you have computed this polynomial g x1 xn epsilon over the field f of epsilon, you can ask what is the limit, meaning what is the polynomial computed in the epsilon to the 0 coefficient, if it exists, right? So more explicitly, let's say g you are computing over f epsilon by a circuit of size s over this field f of epsilon. As I said, that you can use these constants arbitrarily in the edges. Now you want to understand epsilon to the 0 coefficient of g, which is h, and we say that then h has approximative complexity s. Okay. So again, let me go through the definition. I have a circuit where I'm using epsilons and 1 by epsilons in the edges arbitrarily and without any cost, and I want to understand epsilon to the 0 coefficient of the polynomial computed, and that h will call has an approximate complexity s. Now it is known that size and size bar, or the approximative size of h, have this relation, that size bar or approximative size of h is upper bounded by size and upper bounded by exponential size. This is because the epsilon degree can be actually exponential. You can show that this can be exponential. And in general, nothing better than this is known. So once you have defined this algebraic approximation, you can ask different questions. And the first question is debordering. So what do you mean by deborder? Given a class C, we want to understand what is C bar, meaning can I find a new class D, which is nice enough such that C bar or border C is inside D. And you can take this class C anything you want, such as VVP, VP, depth 3 diagonal, VP, and so on. In fact, it turns out that these questions are asked and nothing is in fact known. For example, is border VVP equal to VVP, whether border VP equal to VP, whether border VNP equal to VNP, nothing is known. And now, once you have defined the border class, you can, in some sense, strengthen valence conjecture and say the same thing, whether the proof VNP is not contained in VVP bar and VNP is not contained in VP bar. Equivalently, border determinant complexity or border algebraic circuit approximately circuit size of permanent should both be superpolynomially large. Now, let's look at what are the results known and why are we even looking at these different results. So that the first result known is due to Nissan back in 1991. It is known that VVP equal to border VVP in the non-commutative setting. Not defined what they mean by non-commutative setting, but it is sort of known. It is also known that if you look at depth 3 diagonal circuits and take the border, that means sum of powers of linear forms, and then you take the border of this class, then it is contained in VVP. In fact, we also know that these depth 2 algebraic circuit classes are closed in the sense that if you take the border, you get the same class. Now, why this is important, these deborder results? This is because this is sort of an upper bound result, and upper bound and lower bound is sort of dual to each other. If you can prove strong lower bound, you can prove strong upper bounds and vice versa. So as I already mentioned, in GCT, proving lower bound is the most important goal. So to understanding upper bounds will definitely help to prove strong lower bounds. Okay, so now once I have sort of given an overview of what is GCT and these basic definitions, let's get back to depth 3 circuits. So what is a depth 3 circuit? Sigma pi sigma. Sigma pi sigma with often in K, we denote it as sigma K pi sigma. This essentially computes polynomials of the form sigma pi Lij. So sum of product of linear polynomials. Okay. So the question is, how powerful are these depth 3 circuits? Are they universal? Can they compute everything? It turns out that they cannot compute everything. In fact, if you look at the inner product polynomial on K plus 1, 2 times K plus 1 variables, then you can show that it cannot be written as a sigma pi sigma circuit with often in K, no matter how the large your D is. It's an impossibility result. However, it turns out by very recently, Kumar in 2020 proved that if you look at the border of sigma pi sigma, the scenario is completely different. It is in fact universal. So what he proved is that if you take any homogeneous n-varied degree polynomial, then it can be computed as a border depth 3 fan-in 2 circuits. However, the catch is that your product fanning, at least from the construction of Kumar, is exponentially large. Okay. So the obvious question comes, what happens if we restrict this D, right? Because exponential D implies the circuit size is also exponential. We want to understand what happens if we restrict the D. So what happens with D equal to poly n? Is it even explicit? It's not clear it is explicit or not. If so, if it is explicit, then is it even in VNP, inside VNP? That's not even clear by the definition, because it can be anything, right? And that is exactly what we proved in this paper. So we proved that when D is poly n, then sigma 2 pi sigma bar or border of depth 3 fan-into circuits is contained in VVP. This means in particular that any polynomial which is in the border fan-into depth 3 circuits of size S can be exactly computed by a poly S cross poly S determinant. Okay, linear projection of. And in fact, it is true if you replace this 2 by any arbitrary constant k, and we introduce DDL technique, divide, derive, induct, and limit. I'll not go into the technical parts, but the proof goes via this sort of flow. We divide, we derive, we induct, and finally we take limit to prove this result. Okay, so once you have deborderized, now let's go back, let's get into some de-randomization results. The question is, can I do efficient PIT? Now, by efficient PIT, we mean that if G is a polynomial, approximate polynomial, and H is the limit, we want to find an A such that the limit polynomial H is non-zero at this point A. So can we, given this sigma pi sigma bar circuit, can we find such a hitting set? Now remember, hitting sigma 2 pi sigma does not suffice, because what may happen is that the limit polynomial may become 0 at the hitting set of sigma pi sigma circuit. However, random A always works. And the reason why it may not hit the hitting set of sigma pi sigma may not hit sigma pi sigma bar is because the relative complexity might be really, really high. But what are the known results? Let's see in the border PIT. So we know the depth to PIT, we know depth to PIT because pi sigma bar is pi sigma. We also know sigma with sigma bar depth 3 diagonal PIT even in the border class. Now, Saxena proved into the order K or polynomial size hitting set for sigma pi sigma when top fan in is constant, but it does not unfortunately work in the border class. As I said, due to high complexity difference. And in fact, if you remember the previous result, we show that sigma pi sigma bar with constant top fan in is in VVP, but we do not know efficient PIT for VVP or determinant. So it's not clear if we can de-randomize it efficiently, but it turns out that we can. There is a quasi-polynomial time hitting set for sigma pi sigma bar circuits with top fan in constant. So I'll conclude with these remarks. So the some remarks or some open questions. We showed that this is contained in VVP, this bar. Now can we separate them? So very recently, me with Saxena proved that in fact we can, and that we can actually show an exponential hierarchy. There are circuits which can be computed by sigma pi sigma with top fan in k+1 bar, but cannot be computed. I mean, it requires exponential size circuit if you want to compute it by fan in k. And this, of course, obviously shows this is not equal to VVP, VNP, and so on. So another interesting question is to improve quasi-polynomial hitting set to polynomial time hitting set for sigma pi sigma bar. And of course, the main goal is to extend these results to arbitrary constant depth circuits. Currently, they hold for very restricted depth for depth circuits. Yeah. So that's all I wanted to say. Thank you and stay safe.